Hi, this is Jana Ibrahim's video series on bipolar junction transistor BJT. Let's discuss the common emitter configuration. The common emitter is one of the basic transistor configurations. The figure shown here is one example of the common emitter circuit with NPN BJT. In the schematic shown, the emitter terminal is at the ground potential, hence the name is common emitter. The figure below is showing a common emitter circuit with an NPN transistor and its DC equivalent circuit. Let's assume that the base emitter junction or BE junction is forward biased. So, the voltage drop across the junction is the cut-in or turn-on voltage VBE on. In the forward bias mode, the collector current IC is represented as a dependent current source that is a function of IB or the base current. Note that in this case, we are neglecting the reverse bias junction leakage current and the early effect. Therefore, the base current will be equal to IB is equal to VBB minus VBE on over RB. Implicitly, if the VBB is greater than VBE on, the IB or the base current is greater than 0, and if VBB is less than the VBE on, the IB is equal to 0. Let's look at the collector emitter portion of the circuit. Here we can have IC is equal to beta times IB, and then we can write the KVL, which is VCC equal to be IC times RC plus VCE, or VCE equal to VCC minus IC times RC. Here, we also assumed that VCE is much greater than VBE on, which means the base collector junction or BC junction is in reverse biased and the transistor is biased in forward active mode. From the figure, we can obtain the power dissipated by the transistor, which is PT is equal to IB times VBE on plus IC times VCE. But in most cases, we know that the IC is very much greater than IB and VCE is very much greater than VBE on. Therefore, a good first approximation of the power dissipation is PT equal to IC times VCE. But this approximation is not valid in saturation mode. The common emitter circuit configuration provides the current voltage characteristic shown in the figure given. In the graph, the collector current IC is plotted against the collector emitter voltage VCE for various constant values of the base current, which is IB. The curves are obtained from the common emitter circuits, where the VBB source forward bias the BE junction and control the base current IB. Meanwhile, the CE voltage can be varied by changing VCC values. Another view of current voltage characteristic is shown here. Theoretically, the curves are linear with respect to the CE voltage in the forward biased mode. The slope in this graph is due to the base width modulation effect that was first found by J.M. Early, and it is called the Early effect. Here, when the curves are extrapolated to zero current, they meet at a point on the negative voltage axis, where the VCE is equal to minus VA and the VA is called the early voltage. In general, the early voltage VA is between 50 to 300 volts. For any given value of VBE, the VCE increases and the reverse bias junction increases, which means the width of the BC space charge region or the base collector space charge region also increases. This will reduce the neutral base width, or W. A decrease in the base width causes the gradient in the minority carrier concentration increase and increases the diffusion current through the base. Hence, IC, or the collector current, increases as the VCE increase. Let's solve some common emitter configuration circuit. In this example, we are required to calculate the IB, IC, and IE and VCE for the common emitter circuit given. For the circuit, the VBB is equal to 4 volt, RB is equal to 220 kilo ohm, RC is 2 kilo ohm, VCC is 10 volt, VBE on is equal to 0.7 and beta is 200. We can solve this equation by following these steps. At the base emitter BE input loop, write KVL of the BE junction to find IB. Then find the collector current, or IC, from the IB-IC relationship. From there, we can find emitter current, or IE. Here is the solution for the CE configuration with NPN transistor. I hope you get the same answer as shown here. Now let's try to analyze the CE with a PNP transistor. Similar to the previous question, we need to tackle the problem by looking at the input and output side of the CE circuit. At the base emitter loop, write KVL of the EB junction to find IB, or the base current. Then find the collector current IC from the IB-IC relationship. From there, we can find IE. Finally, we look at the output collector emitter output loop. Write the KVL of the EC junction and find the VEC value. Here are the answers for the second example with PNP transistor. That's end our discussion on CE configuration. In this video, we already learned how to solve simple CE configuration for both NPN and PNP transistor. Thank you and see you again in other videos.